Hi everyone. Today we're going to look at the equilibrium expression and a related value known as the equilibrium constant. This is going to help us start putting numbers to the concept of equilibrium. All right, so we're just going to jump in with an example. I've asked you in a problem here to write the equilibrium expression for, and I've given you 3 reactions to do that for. The equilibrium expression is kind of like an equation. So when we're asked for the expression, we're not plugging anything in. We're just kind of generating that equation that applies to this reaction. The way every equilibrium expression works is the symbol for the equilibrium expression is K, or for the equilibrium constant, but we'll get to that in a moment. The K value is going to always be equal to whatever the concentration of the products are, raised to the power of their coefficients, and those can be, 1, 2, 3, 4, 5, whatever. The products raised to their coefficients over the concentration of the reactants raised to their coefficients. Okay, so it's always products over reactants, and that's going to be important. We're going to say that a lot over the next few weeks. So products over reactants raised to their coefficients. So let's just do these examples. So we've got K is going to be equal to, we've got the only product we have is ClO2, and we're going to raise that to the second power because there's a 2 in front of it. And then the reactants, when you have 2 reactants or 2 products, everything multiplies. So you've got O2 concentration raised to the second power times Cl2 concentration. All right? Notice that these are gases, so sometimes instead of thinking of them in terms of concentration, we'll think of them in terms of pressures. Some people get really hung up on this. I personally don't care because I think it's silly. The main reason I think it's silly is because the answer is almost exactly the same. So it's just in terms of pressure. So I'm going to scoot this over because this answer is going to be fine for most situations, in my opinion. But sometimes you'll see people write this as the pressure of ClO2 squared over the pressure of O2 squared times the pressure of Cl2. All right? So that's a pretty common thing that you're going to see anytime we're dealing with gases and there are pressures involved. Okay. Again, I personally don't care. We'll get to the subtle differences between these 2 versions of this expression at a later date. All right. So now let's look at the second example here, where we've got hydrofluoric acid dissociating into H plus and F minus ions. And in this case, again, it's just going to be products of reactants. So we're going to write K equals H plus times F minus concentration over HF concentration. All right. Again, you have 2 products here. They're going to multiply here in this expression. So for some reason, oftentimes at the beginning, students want to put a plus sign here. There's no plus. It's a multiplication. All right. This last one here brings up an interesting issue. Notice that the water here is in the liquid form. Solids and liquids, basically their concentrations don't change, all right, during a reaction because think about what concentration means. It's the number of particles per volume, right? So a liquid can't get more particles per volume because it just depends on its density, okay? So the way we get around solids and liquids concentration is we just pretend that their concentration equals 1 and we move on with life. There's a subtle, there's some subtlety here that you don't need to worry about at this level. If you take some advanced coursework, we'll talk more about this. But solids and liquids, we're going to pretend like their concentration is 1. It's going to make everything work out a lot better. So when we write the equilibrium expression for this reaction, the point is that we would write this as K equals NH4 plus times OH minus concentration over NH3 concentration times the water concentration, quote unquote, in air quotes, which is just 1. Well, you don't even have to write that because if you multiply something by 1, it doesn't change anything, right? So we can just write this simply as over NH3. All right. So anytime you see a solid or liquid, you can just pretend its concentration is 1 and move on. Now, notice that it's liquid, not aqueous. So aqueous solutions, they appear because we're talking about the solute concentration. That can change. The concentration of the water itself cannot. All right. So now, so that's equilibrium expressions. We're going to get later on into what these equilibrium expressions, these all have specific letters, which we'll deal with. This one would be a Kc, this would be a Kp, this would be a Ka. C for concentration, P for pressure, A for acid. This is a B for base. We will get into the differences between these later on. I only mention it here in case you're watching this video after we've already learned those things. Okay? All right. The second part of this is to understand what the value of the equilibrium constant means. So I've asked you a question here, is the concentration of the reactants or the products greater at equilibrium for these two reactions? So let's just write our equilibrium expression for this, for part A. So that would be H plus times Cl minus concentration over HCl. And notice that that's all equal to 35, okay? So if that's the case, this is going to end up meaning way more products at equilibrium. The reason is, notice that the equilibrium expression is a fraction, right? So you've got a numerator and you've got a denominator. And if the value is a relatively large number, so pretty much anything greater than 1, you're going to have more, your numerator has to be bigger than your denominator. If your numerator is bigger than your denominator, that means, because these are all the numerator is the products concentration, there's a greater concentration of products at equilibrium. Okay? So, because K is greater than 1, the concentration of the products is going to be greater than the concentration of the reactants at equilibrium. All right? Now, that may not be true initially, but once the system reaches equilibrium, this will be the case. Okay? So, let's look at a counterexample. So, HF. One thing before I move on, part A here, remember from first semester, we would have looked at HCl and said, oh, that's a strong acid, right? That completely dissociates in water. And so it makes sense that there would be more products at equilibrium than there are reactants, just based on our first semester knowledge. But now we're putting a number to it, and that's going to help us with some other situations. Okay, or a broader set of situations. All right, so HF, remember first semester is a weak acid, so we would expect it's mostly going to be in the HF form, not the H plus in the F minus form, but let's do this using our equilibrium understanding now. So K equals H plus times F minus over HF, and that's all equal to 4.0 times 10 to the minus 4. So that is a number that's a lot smaller than 1. So that means that you've got to have a bigger denominator here than your numerator, right? If you get a number smaller than 1, you have a fraction like 1/4, right? So 1/4 is smaller than 1 because the denominator is bigger than the numerator. So to get a number like 10 to the minus 4, so 0.00004, you would have to have a much larger denominator, which is a reactant, than you would have your numerator, which is your products, okay? So here we're going to say because K is less than 1, and it's quite a bit less than 1, we're going to say that the reactant concentration is going to be greater than the product concentration at equilibrium, all right? And so somewhere in your notes, you should make a note of kind of these two statements, but this is not something you want to try to memorize. You always want to be able to work it out from, okay, K is a ratio of products to reactants. If K is greater than 1, the numerator is heavier, right? That's going to be a greater amount of products because K is always products of reactants, okay? So you should be able to do it from that, but you also want to be able to summarize these quickly in your notes somewhere, all right? Okay, that is those are the main concepts for equilibrium constants and the equilibrium expression. We'll be using these a lot moving forward, and you'll get lots of practice at this. Hope this was helpful. Thanks for watching. Bye-bye.